Hello there, and welcome to Life Beyond Seen, where curiosity slows to a comfortable drift, and science settles into a quiet, steady rhythm meant to help your thoughts unwind. Tonight we're stepping into a topic that feels both remote and strangely intimate, because it pulls at the part of us that wonders what waits in places the world has barely touched. Beneath Antarctica, far under the frozen surface where the wind never reaches and the sunlight never slips through, there are vast caverns, dark waterways, buried mountains, tunnels carved by forces older than anything we can easily picture. They form a hidden world that scientists long to explore, yet reaching it is almost impossible, not because of myths or rumours, but because the Earth itself has sealed it away behind a barrier of cold, weight, distance, and danger. Before we descend into all of that, I'd love to know where you're listening from tonight and what the weather is like in your corner of the world. Maybe it's warm, maybe it's raining, maybe you're wrapped in blankets or stretching out after a long day. No matter where you are, I'm glad you're here, and if this quiet journey feels soothing or interesting or simply a welcome pause, it would mean a lot if you liked the video or subscribed, so this little calm space can find others who might enjoy it too. And now, as you settle in and breathe a little slower, we can start easing our way toward that hidden environment beneath Antarctica, not rushing toward it, not pushing aside any thoughts, just letting the path unfold a step at a time. The idea of caverns beneath a continent might sound like the start of a legendary adventure, but Antarctica really does hide a landscape more complex than most of us ever imagine. The ice sheet that covers it is more than a frozen surface. It's a giant, moving, shifting mass, thicker than almost any other natural barrier on the planet. In some regions, it's more than 3 kilometers deep, a silent, crushing weight pressing down on mountains, valleys, ancient riverbeds, and entire networks of tunnels held in darkness for millions of years. Explorers have always dreamed of entering these spaces directly, walking through the hidden chambers that lie below, tracing the paths carved by water or volcanic heat, hearing the strange echoes that might bounce between frozen walls. But the truth is far more stubborn than the dream, because almost nothing in that environment cooperates with the tools we have today. Before anyone can even think about sending a person down there, an enormous list of problems waits above the ice, each one more complicated than it seems at first glance. The surface itself is already a challenge. Antarctica is the coldest place on Earth, capable of temperatures that shut down equipment in minutes. The wind can slice across the plateau with enough force to bury vehicles and shred cables. Even reaching a stable spot to set up the machines needed for drilling takes time, planning, and a kind of patience that doesn't usually fit with the idea of exploring caves. The ice has no interest in staying still either. It shifts, cracks, moves, and creaks, as if alive in a slow-motion way that scientists understand well but can never fully predict. A cavern discovered one year might change shape the next, or collapse under its own weight, or seal a passage completely without warning. That means crews working on the surface must always be ready to adapt, to pack up equipment, to rebuild structures, and to accept that some routes into the deep ice will stay closed forever. And even after all of that, the real barrier still sits below. Imagine trying to reach a cave system locked behind thousands of meters of ice, much of it compressed into a solid mass harder than concrete. Tools that work well for rock don't behave the same way in ice. Tools that melt their way downward risk refreezing before they can advance. Tools that drill have to be protected from cold that turns lubricant into sludge and metal into brittle shards. Every method has a limit, and every limit grows sharper the deeper the system goes. What makes this even more complicated is the fact that scientists can't aim for a landmark they can see. Everything beneath the ice must be mapped using signals that bounce through layers of frozen water, and those signals bend, scatter, weaken, and return incomplete. That means the hidden caverns are more like faint outlines than clear destinations. Even when we know they're there, we don't know their shape, their stability, or their exact position. and missing a target by just a few meters could mean the difference between reaching a chamber and drilling into a dead end. Once the first centimeters of ice are broken, the pressure becomes another problem. Ice at the bottom of the sheet is under immense force. It isn't like the snow on the surface. It isn't even like ice cubes in a freezer. It's a dense, ancient material pushed downward by everything above it. When a drill reaches that level, the reaction can be unpredictable. The water released from melting the ice can instantly refreeze, trapping equipment. The surrounding area can collapse inward. Worse, the meltwater can flood upward with surprising speed, filling the shaft and destroying anything in its path. Engineers know how to model these possibilities, but the ice sheet is a living structure in its own slow way, and models never capture its full personality. Even with perfect drilling, the descent itself is dangerous. Sending a human being down a shaft cut through kilometers of ice isn't something we can do safely, so robotic probes are used instead. Those machines have to endure pressures that would crush most metal frames. They have to generate enough heat to move through frozen walls, but not so much that they boil the water behind them. They need strong communication systems, even though radio waves die quickly inside ice. Some designs use fibre optic cables, but cables can snap, freeze, or become trapped. If a robot gets stuck down there, it's almost guaranteed to be lost forever. The cold will shut it down long before anyone can retrieve it. Every mission is a gamble, one where each meter downward increases the odds of losing everything. As if all of that weren't enough, the subglacial environment itself holds dangers that are difficult to predict. Beneath the ice are lakes that have gone untouched by sunlight for millions of years, rivers that move slowly under enormous pressure, volcanic heat that melts pockets of space into large water-filled chambers, and deep caverns that may contain gases or minerals we've never encountered in such isolation. Entering one of these areas without contaminating it is another challenge on its own. Even a single bacterium from the surface could disrupt the fragile balance that has existed there for ages. Scientists must sterilize equipment thoroughly, but even with intense precautions, the possibility of contamination remains. This forces teams to move more slowly, to test every system, to examine every surface, and to restart entire plans if even a minor mistake occurs. Despite all of these obstacles, the curiosity remains. People want to understand the hidden structures beneath Antarctica, not because of fantasy or speculation, but because these caverns hold clues to Earth's past and to environments that might resemble worlds far beyond our planet. Lakes sealed away for eons could contain microbial life adapted to extreme isolation. Their chemistry might mirror what exists under the icy surfaces of moons like Europa or Enceladus. Caverns shaped by volcanic heat could help us understand early Earth, when conditions were harsher and more unstable. Every corner of that hidden world has potential to teach us something meaningful, something patient, something that waited through long frozen ages without ever asking to be discovered. The desire to reach these places grows each year, yet the forces keeping us out remain overwhelming. Not symbolic forces, not mythical guardians, but physics, cold, pressure and isolation. Each one holds its ground with quiet certainty. And as we move deeper into the reasons behind this near impossibility, we find ourselves slowly stepping toward the broader landscape of Antarctica itself, the vastness of it, the silence, the weight of its ancient ice, and the long, slow journey that anyone must take before even thinking about the caverns that linger far below. If you're comfortable, we can keep easing forward from here, letting the path deepen as we move into the strange complexity of this continent of secrets wrapped in white, where everything above and below the surface carries a story that has waited a very long time to be told. Antarctica stretches across the bottom of the world like a quiet, immovable thought, wrapped in a silence so deep that even the wind seems to hesitate before crossing it. From a distance it looks simple, a smooth white shape on a map, a blank place where nothing moves and nothing grows. But that simplicity is only a disguise. The closer you look, the more the continent reveals its complexity, layer after layer of secrets held beneath snow, ice and cold, so extreme it stops machines and reshapes the very ground. Standing on the surface, even for a moment, gives you a sense that everything here has its own intention. The ice shifts, the air tightens, and the land beneath your feet feels older than anything you could compare it to. Before anyone can even begin to think about the caverns hidden below, they have to understand the personality of this frozen continent, because every difficulty, every impossible challenge, begins with the nature of this place itself. Antarctica is enormous, far larger than most people realise. It's nearly twice the size of Australia and holds 90% of all the ice on Earth. If you were to imagine the continent without that ice, the land beneath it would be a jagged, mountainous, uneven shape, with deep valleys, sunken basins, and entire ridges that would qualify as major mountain ranges anywhere else. But the ice is so thick, so dominant, that almost none of this landscape is visible. Everything is covered by a frozen sheet that in some regions reaches more than 3 kilometers downward. You could stack the tallest skyscrapers on top of one another and still not reach the surface. That makes Antarctica a continent hidden beneath its own shield, shaped by a weight that has pressed down on it for millions of years. The ice didn't appear overnight. Over long ancient periods, snowfall accumulated layer by layer, compressing under its own mass until each flake turned into dense, compact ice. As more snow fell, more layers formed, building a massive, slow-moving, continent-sized glacier. Over time, this glacier began to flow outward from the high central plateau, pushed not by speed but by gravity. In some places, the movement is only a few meters per year. In others, where the ice funnels through narrow canyons, it slides faster, stretching and cracking like thick glass. The surface looks still, but it's never truly at rest. It moves in a steady crawl, pushing toward the edges until it meets the ocean, where it breaks into icebergs that drift away and melt far from their birthplace. This slow outward flow is one of the reasons the caverns beneath Antarctica stay so unreachable. Anything buried under the ice moves too, carried along like a grain of sand trapped inside a massive conveyor. Even if you found a cavern one decade, it might shift out of reach the next. Scientists have to account for all of this movement when trying to model what lies beneath. Every measurement taken at the surface has to be corrected to account for the direction and speed of the ice around it. It's like trying to study a building while standing on a conveyor belt, and the building itself is moving on another conveyor belt beneath your feet. Then there is the cold, a kind that doesn't just sting for a moment but pushes into every material and structure with relentless persistence. Antarctica holds the record for the lowest temperature ever recorded on Earth. In some places inland, far from coastal winds and moisture, the temperature can drop below minus 80 degrees Celsius. At that level of cold, metal becomes brittle, plastic shatters, batteries die rapidly, and even the oil inside machines thickens to the point of being nearly useless. Teams working on the continent have to heat equipment constantly, insulate every exposed surface, and design protective layers that most other environments would never require. When researchers travel across the Antarctic interior, they bring backup parts for their backup parts, simply because the cold is so efficient at destroying anything created by human hands. Weather conditions add another layer of difficulty. Although Antarctica is covered in ice, it's technically a desert, receiving very little precipitation. That dryness helps shape some of the clearest air on the planet, but it also means windstorms can sweep across the plateau with surprising ferocity, picking up powdery ancient snow and flinging it across the surface in long sheets that obscure everything. Visibility can drop to almost nothing, structures get buried, ridges disappear, navigation becomes a matter of trusting your instruments rather than your eyes. And because this happens often, research teams must be trained to operate in conditions where they can barely see a few meters ahead of them. All of this might make the continent sound hostile, but it's more accurate to say that Antarctica simply follows its own rules. It doesn't push people away intentionally, it just continues doing what it has always done. The the ice advances. The winds reshape the surface. The cold erases footprints and reminders of human presence in a matter of hours. Everything is built on top of a foundation that appears steady, but is actually shifting very slowly under enormous pressure. And this shifting doesn't only affect the surface, it influences what lies beneath as well. Below the ice is a network of features so complex that even the most detailed maps are only approximations. Mountains that rise sharply from the base rock, valleys that once held rivers before the ice buried them, and basins where water has collected in large hidden lakes that remain liquid due to pressure and geothermal heat. The largest of these lakes, Lake Vostok, is the size of a small country and has been sealed beneath nearly 4 kilometers of ice for millions of years. Dozens of other lakes, some connected by subglacial rivers, exist throughout the continent. Every one of them is isolated, untouched and protected by the ice above. The existence of liquid water so far below the surface was once only speculation, but radar surveys and seismic readings confirmed it. And once scientists realized what was down there, the continent took on an even more mysterious character. Suddenly, Antarctica wasn't just a frozen surface. It was a place where entire ecosystems might be hiding, locked away in total darkness, in water that hasn't seen the atmosphere since before humanity existed. If life survives in those lakes, it must be adapted to extremes that defy almost every known biological rule. That makes these hidden bodies of water some of the most scientifically valuable locations on the planet, and also some of the most protected. No one wants to disturb a system that might reveal insights into life on early Earth or on icy moons beyond our planet. Even with this knowledge, reaching the ground beneath the ice remains a monumental challenge. The ice sheet is so thick that direct drilling is incredibly time-consuming. Projects require years of preparation, planning, and environmental safeguards to prevent contamination of any subglacial environment. When a team does attempt a drilling project, they must bring enormous quantities of fuel, specialized equipment, sterilization systems, insulation, and modular infrastructure capable of surviving months in some of the coldest and most remote locations on the planet. The logistics alone are staggering. Everything must be flown in or hauled by convoy across hundreds or thousands of kilometers of rough terrain, and once something breaks, repairs must be made with the materials already available. There are no hardware stores or supply depots. Every part must be accounted for in advance. The continent is divided physically as well. The mountains of the Transantarctic range cut across it like a spine, separating East Antarctica from West Antarctica. The ice flows differently on each side. The bedrock beneath has different elevations and geological histories. Volcanic activity in certain regions melts portions of the ice from below, forming hidden cavities filled with warm water or gas. Some of these cavities may resemble caves, though the word doesn't fully capture how strange these subglacial spaces can be. They are shaped not by air and erosion, but by pressure, heat, and the slow grinding force of ice that never stops moving. These variations mean that no two regions of Antarctica behave the same way. A drilling technique that works in one sector might fail completely in another. A measurement taken near the coast might not apply at all to the plateau. Even the thickness of the ice changes dramatically. In some areas, you could theoretically reach the bedrock after drilling through a few hundred meters. In others, the ice extends farther downward than the height of many mountain ranges. This uneven landscape forces anyone studying the continent to treat it not as one uniform environment, but as a patchwork of interconnected but distinct systems, each governed by its own conditions. Yet for all of its complexity, Antarctica has a strangely calming presence. The silence, the vastness, the unbroken horizon, and the feeling of standing on something that has existed in its frozen state for so long creates a sense of humility. There's no rush here, no hurry. Everything moves in slow cycles measured in centuries and millennia rather than minutes or hours. The wind may be fierce, but the deeper rhythm of the continent is slow and steady. For researchers who spend long seasons here, That rhythm becomes part of their work. They wake, measure, observe, repair, prepare, and continue with tasks that require patience more than speed. Understanding Antarctica is essential before imagining what waits beneath it. The surface is the gatekeeper. The cold is the filter. The ice is the shield. Every difficulty that arises in the pursuit of exploring subglacial caverns begins with this vast, quiet environment, a continent wrapped in white, holding its secrets until the moment the world is finally prepared to meet them with the care they require. And as we move deeper into this journey, the next step brings us closer to the unreachable depths under that frozen shield, where all the challenges of surface exploration begin to converge into an even more formidable barrier waiting below. Beneath the endless white surface of Antarctica lies a depth so remote that even imagining it requires a moment to adjust your expectations. Most places on Earth have a bottom you can picture. Soil beneath grass, rock beneath soil, maybe caverns beneath the rock. Here, the bottom is not something you can simply visualize. It's hidden under a frozen shield so thick, so dense, and so unyielding that reaching it is sometimes compared to drilling through a small mountain placed upside down beneath your feet. The deeper you go, the stranger the conditions become, and the more the limits of engineering begin to show. Even the most advanced tools humanity has built struggle in an environment so cold, so heavy, and so isolated that it reshapes metal, bends structures, and shuts down instruments that work flawlessly everywhere else. And before anyone can even think about entering the caverns beneath the ice, they must first contend with the immense barrier that sits above them. It helps to start with the scale. The Antarctic ice sheet is not a thin crust. It's an entire geological feature, with thicknesses that reach well over 3,000 meters in many parts. Imagine standing on a layer of frozen water taller than most mountain ranges. Each meter below you increases the pressure, the weight, the density, until the ice at the bottom becomes something entirely different from what most people would recognize. It isn't loose or airy, it isn't fragile. It's a solid, compact mass shaped over millions of years, pushed downward by everything above it. Snow falls, compacts, hardens, and sinks, creating layer after layer that slowly becomes part of the shield. Each layer holds a whisper of previous climates, ancient atmospheres, distant global conditions, and even particles from faraway volcanic eruptions. But those layers, while scientifically rich, also reinforce the massive barrier that makes the depths nearly unreachable. When scientists attempt to drill downward, they're not cutting through soft frost. They're trying to penetrate ice that has the density of rock, yet behaves differently from any solid they've handled before. At certain depths, the ice flows like an extremely slow-moving fluid. At other depths, it's brittle and cracks under stress. And deeper still, it becomes so compact that it's difficult to predict how it will react to heat or pressure. The deeper the drill travels, the more it's squeezed by the surrounding ice, as if the continent itself is trying to close the path behind it. The hole begins to narrow. The meltwater created by some drilling methods refreezes quickly, forming new layers that trap equipment unless constant heat is applied. Tools must be designed to account for this narrowing, and even then the environment has a way of turning simple expectations into complicated setbacks. Reaching the depths is not only a challenge of method but also of time. A drilling operation capable of reaching the full thickness of the ice sheet requires weeks or months of non-stop work. Crews must operate in shifts, monitoring the system day and night, because stopping the process for even a short period can allow the borehole to freeze shut. Fuel must be transported in massive amounts, sometimes by convoys that take weeks to cross the continent. Equipment must be maintained constantly, and even a minor mechanical issue can delay progress by days or weeks, because the cold punishes every exposed component. Metal contracts, wires stiffen, hoses crack, lubricants thicken until they can hardly flow. Every piece of machinery is tested repeatedly, Not because the teams expect to make mistakes, but because Antarctica finds ways to cause problems without warning. Even if everything goes well, every layer of ice behaves slightly differently. The uppermost layers are clean and white, composed mostly of compressed snow that still contains pockets of air. The deeper layers are darker, containing microscopic particles that have been buried for tens of thousands of years. They create friction, cause sensors to misread, and introduce unpredictable changes in the ice's texture. As the drill descends further, temperature and pressure increase. The ice grows warmer, not because the sun reaches it, but because geothermal heat seeps upward from the Earth's crust, and because the weight above compresses the ice so much that it begins to deform under the pressure. This warmth is subtle, only a few degrees above freezing, but it's enough to create thin films of water that can slide along surfaces or freeze into irregular shapes that complicate the descent. The most important thing to understand about these unreachable depths is that they are not empty. Beneath the frozen shield lies a landscape shaped by forces that have been at work far longer than our species has existed. The bedrock isn't flat. It rises into mountains and drops into deep valleys. The ice flowing above follows these shapes, pressing into crevices, filling submerged basins, and creating hidden pockets where meltwater collects. These pockets can become interconnected, forming subglacial rivers that flow under tremendous pressure. Some of these rivers carve tunnels through the ice, while others gather in low points to form lakes that remain untouched by the outside world. Each one is sealed so thoroughly that even the smallest disturbance risks altering an environment that has remained stable for millions of years. Reaching those lakes requires drilling not only through ice, but also into an isolated ecosystem. That introduces a new set of difficulties, because anything entering the water must be completely sterile. A drill that brings contamination from the surface could disrupt the ecosystem or destroy valuable scientific evidence. To prevent this, teams must use sterile fluids, carefully filtered water, and equipment that has been cleaned to extreme standards. This slows progress even further. Every action must be calculated. Every material must be approved. Every tool must be tested for leaks, microfractures, chemical reactions, and compatibility with both ice and the water expected below. Then there is the question of pressure. Ice weighs more than rock when compressed over great thicknesses. At the bottom of the sheet, the pressure reaches levels that can crush unprotected equipment instantly. Drilling fluid must be carefully balanced to prevent the borehole from collapsing inward. If there isn't enough pressure inside the shaft, the surrounding ice will squeeze it until it closes. If there's too much pressure, the lower sections might fracture. Achieving the right balance is a delicate process that requires constant calculations. Scientists measure temperature, density, flow rate, and pressure fluctuations at every stage. They adjust the system frequently, and despite all of this, the ice can still behave unpredictably, shifting slightly in response to the borehole, altering its shape, or moving meltwater through channels that weren't present moments before. All of these challenges exist before anyone even reaches the cavern systems themselves. And the caverns are not the broad stone chambers familiar from movies or legends. They are narrow, twisting, pressurized spaces shaped by meltwater and geothermal heat. Some are filled with water, some are half frozen, some are empty pockets created by volcanic activity. Others are more like long tunnels than open rooms. Radar shows their presence, but rarely their exact shape. Their walls might be thin enough to collapse under minimal disturbance. Their temperature might hover so close to freezing that a small change in pressure could cause rapid ice formation. Their entrances might be so narrow that a robotic probe cannot pass, even after all the difficulty of drilling down to reach them. But perhaps the most daunting problem is communication. Once a robot is sent into the depths, its connection to the surface becomes fragile. Radio signals cannot travel through thick ice. Cables can freeze or snap. Fiber optics must withstand intense pressure and shifting ice. And if a robot becomes trapped in a tight passage or stranded in a flooded chamber, retrieving it is virtually impossible. There is no way to send a human rescuer. No way to widen the passage without risking collapse. No way to stabilise the surroundings long enough for a complex manoeuvre. A lost robot becomes a permanent fixture of the subglacial world, frozen into a place that will remain sealed long after the rest of the world changes. Still, the desire to reach these unreachable depths persists. Scientists push forward because these environments hold answers to questions about Earth's history, climate, geology, and possibly biology. They continue because the unknown has always drawn human curiosity. They design better drills, better probes, better models. They work in the harshest conditions imaginable, because the reward, one clear sample of water from a lake untouched for millions of years, one visual of a cavern shaped entirely by natural forces hidden from the sun, is worth the effort. As the barriers become clearer, the path forward does not shrink. It becomes more defined, and each step down into this frozen world helps reveal not only what lies beneath the ice, but also why exploring such spaces requires patience and an understanding of the obstacles that wait deeper still. The next layers we approach bring us closer to the reasons Antarctica's ice refuses to let us in, forming a shield that tests every capability we have and reminding us just how far we still have to go before these depths become reachable at last. Antarctica's ice behaves like a guardian that never sleeps, not because it chooses to protect the world beneath it, but because its nature makes entry nearly impossible. Anyone standing on the surface sees only a flat expanse of white, stretching outward in every direction. But the ice is not a quiet blanket. It is a constantly shifting mass with its own movements, its own stresses, its own locked-in energy that creates barrier after barrier for anything attempting to pass through it. The difficulty isn't just that the ice is thick, it's that the ice is alive in a slow, physical way that resists every intrusion, every instrument, and every attempt to reach the spaces under it. The first thing that must be understood is that Antarctic ice isn't a single uniform type of frozen water. It is layered history. Every snowfall that landed over hundreds of thousands of years became part of a vertical timeline. The upper layers are crisp, clean, and almost friendly compared to what lies deeper. But the deeper you go, the more the ice turns into a compressed, hardened substance so dense that it behaves less like ice and more like a strange transitional material between solid and liquid. This difference alone makes drilling unpredictable. The equipment might glide easily through one layer and then hit an area so tough that it takes hours to advance a few centimetres. The resistance isn't consistent. It changes with depth, temperature, trapped particles, pressure, and the slow deforming movement that takes place within the sheet. Ice doesn't remain still under its own weight. The deeper layers move outward like thick syrup pushed beneath a lid. This movement happens so slowly you'd never feel it beneath your feet, yet it continuously shifts the structure of the sheet. The pressure changes, the thickness changes, the stress lines shift. When someone tries to drill into it, they are working with a material that behaves differently every few hundred meters. This makes planning extremely difficult. A drilling method that works smoothly in one location can struggle in another, and even two boreholes placed close together can encounter different obstacles, because the ice beneath them is flowing at slightly different rates. Temperature is another reason the ice resists entry. The surface is brutally cold, cold enough to stop machines, crack metal, freeze fuel, and turn the simplest task into a struggle. But as you travel downward, the temperature rises due to geothermal heat. This warmth is not enough to melt the ice entirely, but it is enough to change how the ice responds to force. In the upper layers, drilling can cause the ice to fracture suddenly. In the middle layers, it may flow slowly inward as pressure increases. In the deepest regions, it may partially melt around equipment, only to freeze again moments later, trapping machines in place. This transition from brittle to plastic to viscous makes the ice an adversary that behaves unpredictably at nearly every stage of the descent. Even if scientists design machines that can tolerate freezing temperatures, intense cold still attacks them constantly. Lubricants thicken until they barely move. Hydraulic systems strain. Electronic components become sluggish or fail entirely. Batteries drain far faster than they would under normal conditions. A drill that works perfectly in a lab can seize up after a short time in the Antarctic interior. Engineers compensate for this with heaters, insulated cabling, and protective coverings, but every added layer increases complexity and weight, and the deeper the equipment goes, the harder it becomes to maintain the right internal temperature. A machine that's too warm will melt surrounding ice and risk becoming trapped. A machine that's too cold will freeze and shut down. Finding the balance between the two is a constant challenge. Then there is the pressure. At great depths, the ice above exerts an enormous downward force. This pressure squeezes anything inside it, from air pockets to meltwater to the walls of a borehole. A drilled shaft must be supported and filled with a fluid that can withstand this pressure while keeping the walls from collapsing inward. If the fluid is too light, the ice compresses the hole until it seals shut. If it is too heavy, the fluid can push outward and fracture the surrounding layers, creating cracks or causing meltwater to rush upward. Maintaining balance requires constant monitoring. Teams must measure the density of the drilling fluid, the temperature of the surrounding ice, the flow rates, and the pressure levels at various depths. All of this must be done while working in a place where storms can delay operations for days and equipment can fail without warning. Even when progress is smooth, the ice has another way of resisting: refreezing. Drilling into Antarctic ice often involves heat, because melting through it can be faster than cutting or grinding. But melted water doesn't stay liquid for long. As soon as heat is removed, the water around the drill begins to freeze again, creating new layers that trap machinery in place. The deeper the drill goes, the more difficult it becomes to prevent this refreezing from closing the shaft. Some teams pump warm water continuously, but that requires massive heating systems, large quantities of fuel, and constant oversight. And even then, if drilling pauses for just a short time, the entire shaft can freeze and become unusable, turning weeks or even months of work into a solid cylinder of ice. A unique problem arises when drilling approaches the bottom of the ice sheet. Because the ice is under such intense pressure, any small pocket of meltwater trapped inside can respond explosively when disturbed. Even a small disturbance can cause water to surge upward through the borehole at high speed, flooding equipment, freezing in place, or destroying instruments. This makes the final stages of drilling some of the most dangerous. Teams must slow their progress, increase monitoring, and prepare for rapid shifts in pressure. This caution is necessary not only to protect equipment, but also to avoid disrupting the environment beneath the ice. The ice also resists entry in more subtle ways. Over time, shifting glaciers create internal shear zones. These zones are like invisible fault lines within the ice. When a drill passes through one, everything becomes more complicated. The ice in these zones is often fractured in strange ways. It may contain dust layers, volcanic ash particles, or ancient compacted snow layers with different melting points. A drill moving through such a zone can suddenly tilt, encounter unexpected resistance, or lose stability. Instruments that map the ice from above can identify some of these zones, but they can't predict how the zones change or how wide they are. Once drilling begins, the team must respond in real time, adjusting direction, method, and technique to accommodate a medium that refuses to behave in a uniform manner. The deeper the drilling effort goes, the more logistical challenges arise at the surface. A drilling camp must remain functional in extreme cold for long stretches of time. Fuel must be kept unfrozen, which often means keeping it heated or stored in insulated tanks. Workers must cycle in and out of heated shelters, because exposure to the wind can cause frostbite in minutes. Machines need constant repairs. Communication equipment must remain clear of ice buildup. Even the simple act of keeping a drilling tower upright becomes difficult when the snow beneath it shifts or drifts pile up around the supports. Antarctica forces every system to work harder simply to remain operational. As difficult as all of this is, the greatest challenge might be the requirement to keep the subglacial environment uncontaminated. Any drill that punctures the ice must not carry microbes, chemicals, fuel residues, or other contaminants downward. The caverns, lakes, and waterways beneath the ice have been isolated for millions of years. Introducing modern bacteria or microscopic debris could alter these environments permanently. Because of this, every component of the drilling system must be sterilized, often repeatedly. Fluids used in the process must be filtered or replaced with pure, clean water. Tools must be handled with extreme care. Protective coverings must be inspected constantly. Even the air entering certain systems must be filtered to avoid carrying particulates downward. These precautions make drilling slower, more delicate, and more expensive. They also extend the amount of time teams must spend in one of the harshest environments on Earth. Maintaining a fully sterile operation in a place where the ground freezes harder than steel and the wind can bury equipment in a matter of hours is extraordinarily complex. Another reason Antarctica's ice refuses to let us in comes from its ability to hide what lies beneath. Mapping the subsurface is possible through radar and seismic imaging, but these methods have limitations. Radar waves scatter when they pass through certain impurities. Seismic waves reflect unpredictably off uneven layers. Some portions appear almost transparent to scanning equipment, while others distort the data so heavily that scientists must guess what lies below. This uncertainty makes choosing a drilling location difficult. A site that appears promising in surveys might turn out to be filled with unexpected obstacles. Choosing incorrectly can cost years of planning and millions of dollars in equipment. Finally, the ice resists human entry because of the sheer isolation of the place. Reaching a drilling location in Antarctica often involves a journey across hundreds or thousands of kilometers of featureless terrain. There are no towns, no supply stations, no roads. Everything must be brought in from the outside world. If something breaks, teams must repair it on the spot. If weather shuts down flights, resupply might be delayed for days or weeks. This remoteness amplifies every challenge beneath the surface, because whatever happens down there must be managed with the limited resources available above it. Antarctica's ice refuses to let us in not out of intent, but because every aspect of its nature, its thickness, its cold, its pressure, its shifting movement, its unpredictable layers, its ability to refreeze, and its isolation, combined into one of the most impenetrable natural barriers on Earth. Each time humans try to reach the hidden world beneath, the ice responds by complicating the process in ways that force us to rethink, redesign, and prepare all over again. And still, the journey continues, pulling us deeper into the long, patient labyrinth hidden below, where the next part of this path reveals how vast and intricate the subglacial world truly is, stretching into a maze of tunnels and hollows carved out over ages by forces we've only just begun to understand. Beneath the endless white surface, far below the storms, the drifting snow, and the hard crust that defines Antarctica's upper world, there is a landscape so intricate that even scientists who have spent decades mapping it still describe it with a kind of quiet disbelief. It isn't a single cavern or a simple hollow. It's a maze woven into the base of the ice sheet, shaped over millions of years by pressure, heat, movement and water that never sees the light of day. Calling it a labyrinth isn't poetic exaggeration. It's an accurate description of a system so complicated that even the most advanced imaging tools struggle to capture more than fragments of it. This hidden world stretches across the continent, twisting around buried mountains, dipping into ancient valleys, and forming passages and chambers that no human has ever stood inside. And while we can detect parts of it, the full picture remains blurry because everything about this underground network operates under conditions no ordinary environment can match. The ice sheet doesn't sit neatly on smooth ground. The bedrock is wild, uneven, jagged in some places and deeply carved in others. Before the ice ever formed, Antarctica had wide river systems, volcanic regions, plains, ridges and mountain slopes. When the ice arrived, it covered everything slowly, locking entire landscapes beneath kilometres of frozen weight. But the land beneath didn't stop influencing what happened above it. Heat from volcanic activity melted certain portions of the ice from below. Differences in elevation forced the ice to flow faster in some areas and slower in others. Pressure built up in deep valleys. The combination of these forces carved tunnels, widened narrow passages, and opened cavities that now form the bones of this hidden labyrinth. To imagine this network, picture an entire region where water moves in ways that seem impossible on the surface. At the bottom of the ice sheet, temperatures rise enough for thin layers of water to form between the ice and the ground. This water doesn't behave like a normal stream or river. It is squeezed and pushed by the immense weight above it, flowing in channels that shift constantly. Some of these channels head downhill across the bedrock, but many follow paths created by the structure of the ice itself. This creates long corridors of pressurized water that can stretch for tens or even hundreds of kilometers, carving low tunnels with roofs made of solid ice. In some places, the tunnels open into larger cavities, either because the bedrock drops sharply or because geothermal heat has melted more ice than usual. These open spaces don't always fill with water. If the heat source is uneven, some chambers remain hollow, coated in layers of frozen crystals that form when water vapour condenses and refreezes. Others fill partially with slushy mixtures that behave neither like solid ice nor liquid water. Still others hold full lakes, isolated pockets of water so deep and so old that they've been sealed away longer than many modern mountain ranges have existed. These lakes connect to the labyrinth too, because small channels, often no wider than a few centimetres, feed them from different directions. A lake might sit quietly for thousands of years, then suddenly drain through a nearby channel when the pressure shifts, only to refill again decades later from another route in the maze. Although the full layout of this labyrinth remains largely unknown, measurements gathered over decades have revealed enough to understand its scale. Beneath the central plateau are long tunnel-like depressions carved by flowing water under pressure. Along the edges of ancient mountain ranges buried entirely beneath the ice, heat from the ground warms the lower layers enough to create cavernous spaces where the ice lifts just slightly off the rock. These areas resemble massive shelves, with ice arching upward to create hollow regions between the ceiling of frozen water and the bedrock below. Some estimates suggest that certain of these cavities could fit skyscrapers, though of course there is no light or air inside them and no surface as we would recognise it. The labyrinth also contains branching networks shaped purely by the movement of the ice itself. As glaciers push across uneven terrain, the stress creates tension within the lower layers. Ice deforms, stretching in some areas and compressing in others. This creates fractures that can widen into small pathways. When meltwater flows into these cracks, it deepens them, carving miniature canyons within the ice. Over long periods, these narrow paths can grow into long winding corridors. They twist around sharp turns, dip under frozen ridges, and climb over buried mounds of rock. Some may be tight enough that only a small robotic probe could navigate them. Others may broaden into wider expanses formed where multiple melt channels converge. One thing that makes this labyrinth so unique is the way it shifts over time. The ice is constantly moving, even if slowly, and that means the tunnels and cavities move too. A pathway that exists today may lengthen or narrow in the coming centuries. A void may collapse. A lake may drain and become part of a new tunnel system. Because everything is under such immense pressure, small changes in temperature or flow can alter the structure significantly. This makes the network feel alive in a geological sense. It's reshaped not through sudden events that humans would notice, but through persistent forces acting gradually over vast spans of time. Mapping this environment is incredibly difficult. Radar systems can detect where the ice meets the bedrock, but internal cavities are harder to identify. Water-filled tunnels reflect radar in inconsistent ways. Some radar waves pass through them cleanly, while others bounce back. The result is a patchwork of signals that hint at the presence of tunnels without showing their full shape. Seismic imaging helps by sending vibrations through the ice and measuring their reflections, but this too has limitations. The deeper the network, the more interference the ice introduces, and because the pathways vary in size and composition, tying the data together into a coherent map becomes an enormous challenge. All of this means that even after decades of exploration, scientists still only understand a fraction of the labyrinth structure. They know it exists, they know it is vast, they know it connects lakes, rivers, cavities, and depressions, but they cannot visualize it as a complete structure. At best, they see fragments. One channel here, another lake there, a hollow region beyond that. Everything else remains hidden in a complexity that pushes the limits of remote sensing technology. Another part of what makes this labyrinth so unreachable lies in the environment within the caverns themselves. If a probe was somehow lowered into one of the larger hollow regions and managed to move through it, the conditions inside would challenge its survival. The air pressure is minimal because these are not air-filled spaces like terrestrial caves. They are controlled by ice pressure and water behaviour. If a cavity is filled with water, the pressure increases dramatically. If it is empty, the pressure becomes uneven, with the ice above acting as a ceiling ready to collapse. Temperature variations within these spaces are also intense. Some areas may hover near freezing, while others, influenced by geothermal heat, may warm just enough to create humid, unstable surfaces that can refreeze suddenly when disturbed. The surfaces inside these caverns don't resemble rock walls. Instead, they are made of ice shaped over centuries. Some areas would be smooth, polished by flowing water. Others would be sharp, jagged, or brittle, the result of ice fracturing under internal stress. Crystals may form strange patterns, with layers arranged in sheets or spirals. In the places where warm water meets colder layers, frost might accumulate into delicate structures that crack or melt depending on the slightest temperature shift. A vehicle travelling through such an environment would need to navigate terrain completely different from any earthly cave system. There's no gravity-driven sediment to settle on the floor, no stable roof carved out over time, no predictable directions where natural forces have carved wide passages. Everything is shaped by pressure, movement, and heat that behave differently at every point in the maze. Even if a probe entered a water-filled tunnel, movement wouldn't be simple. The water is under pressure. It is cold enough to freeze around any object that lingers too long. There may be floating ice crystals, slushy formations, or sudden changes in flow direction. A probe could drift into a narrow passage and become stuck, or it could encounter a sudden drop where the bedrock descends into a deeper basin. Without a tether, it could be swept away into a branch that no sensor has mapped. With a tether, it could be trapped by shifting ice or moving debris. The very structure that makes the labyrinth exist also makes it unstable for anything attempting to travel through it. Another challenge comes from the fact that much of this labyrinth is sealed by ice that continues to thicken from above. Snow falls on the surface, compacts, sinks, and adds pressure to the system below. This constant addition of mass means the caverns are squeezed slowly over time. Old pathways collapse, new ones form. The shape of the labyrinth is not static. Instead, it adapts to changes in the ice sheet, responding to stresses in ways that are almost impossible to predict without long-term observations. A small shift in temperature higher up can ripple downward through the system, altering the melt patterns. A change in pressure in one lake can influence the flow of an entire subglacial river. Everything is connected in a delicate balance that responds to forces too gradual for the surface world to notice. Despite these challenges, this labyrinth is one of the most intriguing environments on Earth, because it may hold insights into worlds beyond our planet. The conditions beneath Antarctica mirror what scientists expect to find under the icy crusts of certain moons. The isolated lakes resemble potential environments on Europa or Enceladus. The pressurized water networks capture what subsurface oceans might feel like on distant bodies. The caverns, shaped by a mixture of heat, pressure, and water, resemble environments that could exist on planets where surface exploration is impossible. Understanding this labyrinth could help scientists prepare for missions to other worlds, but first they must understand it here, beneath the thick ice that holds it tightly closed. Everything that exists in this network tells a story of ancient climates, buried mountains, trapped water, shifting ice, and forces that reshape the world beneath without ever becoming visible at the surface. This hidden maze explains why exploring Antarctica's underside is not just an engineering problem, but a challenge that requires a deep understanding of geology, ice physics, climate history, water behaviour, and biological limits. As we move forward, we step from the broad picture of this underground world toward a more focused understanding of the strange waterways that flow through it, where subglacial lakes and rivers exist in darkness and isolation, forming environments that remain untouched by human presence and separated from the surface by a barrier so complete that even light has never breached it. Far beneath the dense ice sheet, in a world without light or seasons or any sign that the surface even exists, lie the subglacial lakes and rivers of Antarctica. They are among the strangest bodies of water on Earth, and yet they behave with a quiet consistency shaped by pressure, heat, and isolation so complete that nothing from the outside world reaches them. These lakes and rivers do not freeze solid despite being locked under temperatures that would stop almost anything else. They flow, shift, drain, and refill under a ceiling of ice thicker than the height of nearly every mountain in the world. They form part of a hidden system that operates on timescales we rarely think about, moving slowly through spaces that haven't seen sunlight in millions of years. Before anyone can imagine entering the caverns beneath Antarctica, they must understand these dark waters and the conditions that allow them to exist. At first, the idea of liquid water under a mile or more of ice seems impossible. The surface of Antarctica is so cold that metal cracks, engines seize, and even the most insulated equipment must be heated constantly just to function. But the bottom of the ice sheet behaves differently because of pressure. The weight of the entire sheet presses downward with such force that the melting point of ice decreases. Under normal conditions, water freezes at 0 degrees Celsius, but under massive pressure, ice can remain solid at lower temperatures, and even slight amounts of heat become enough to create thin layers of meltwater. This heat doesn't come from the surface. It rises from the Earth's interior, travelling through the bedrock and into the deepest layers of the ice. Though the geothermal energy is subtle, the pressure amplifies its effect, making it possible for water to remain liquid in pockets, channels and basins deep beneath the continent. These pockets grow over long periods. Some begin as small films of water that lubricate the base of the ice sheet. As more meltwater forms, the films widen. In areas where the bedrock dips sharply, the water collects and deepens. Over thousands of years, this process forms lakes, some of which are enormous in size. The most famous is Lake Vostok, more than 250 kilometers long and buried beneath nearly 4 kilometers of ice. But Vostok is only one of more than 400 known subglacial lakes. Many of them are smaller and remain hidden from view, discovered only through radar surveys, seismic studies, and careful measurements of how the ice above them moves. The lakes don't sit still. Pressure causes the water to shift between them. When one lake accumulates too much water, the pressure builds until it sends part of its volume through narrow channels toward lower basins. These channels act like hidden rivers flowing under the ice. They move slowly, not like surface rivers with open air and gravity-driven speed, but like rivers in a sealed system where every direction is constrained by ice walls and bedrock. Their paths follow slopes in the terrain. Some flow for dozens of kilometers before reaching another lake. Others drain into long tunnel-like depressions carved out over time. The movement of water in the system is difficult to predict because the ice sheet above it is not static. As the ice shifts outward across the continent, the pressure changes. A lake that was stable for centuries might begin to drain suddenly if the ice above stretches slightly. A river that once flowed gently might become compressed between moving layers and narrow into a nearly impassable channel. Scientists studying these subglacial systems have observed lakes that fill slowly over many years and then drain rapidly in a single event. When this happens, the ice above the lake settles downward slightly and satellites can detect the changing elevation. These subtle movements allow researchers to trace the hidden waterways even when they cannot see them directly. The water in these lakes is unlike any water found on the surface. It has been isolated for such long periods that its chemical composition has changed. It carries dissolved minerals from the bedrock below and from the particles trapped within the ice. It lacks any direct contact with the atmosphere. In some lakes, the water is fresh and nearly pure because the ice above it filtered out almost all contaminants. In others, the water contains unusual salts or minerals released by rock under pressure. This variation creates conditions unlike anything in typical lakes or rivers. Each one is an isolated world with a unique chemical signature, shaped by the slow processes of freezing, melting, and geological interaction. Because these lakes have been sealed away for so long, scientists are extremely careful about how they approach them. Any contamination from the surface could alter the environment irreversibly. Even microscopic contamination matters. Introducing bacteria or chemicals not found in the natural system could disrupt chemical reactions that have taken place in stable isolation for millions of years. That's why drilling operations designed to reach these lakes must follow strict sterilization procedures, using purified water, clean equipment, and methods that minimize risk. This creates a challenge, because drilling through thousands of meters of ice without leaving behind contaminants requires careful planning and specialized technology. In addition to the lakes, the rivers beneath the ice form a network that expands far beyond what early researchers imagined. These rivers do not erode the ground in the same way as surface streams. Instead, they interact with the ice, carving internal pathways and influencing the movement of the glacier above. When enough water flows through a channel, it can speed up the flow of the ice sheet, reducing friction between the ice and the bedrock. This can cause portions of the ice to slide more quickly toward the coast. In other places, the water pools, thickens and slows the flow, creating regions of remarkable stillness. Every river and every lake plays a role in shaping how the ice above them moves, and this movement affects the stability of the entire sheet. One of the most fascinating aspects of these hidden waterways is that they may offer clues to the limits of life. Water in these environments is cut off from sunlight, lacks oxygen, and remains under intense pressure. Yet some scientists believe microbial life could exist in certain lakes, sustained by chemical reactions with the minerals in the water. These potential organisms would not resemble surface life. They would survive without photosynthesis and rely instead on chemical energy sources. Discovering such life would expand our understanding of biology and provide a model for life that might exist on icy worlds beyond Earth. The most isolated lakes, like Lake Vostok, present particularly intriguing possibilities. They have remained sealed for so long that any life within them would have adapted to conditions that have changed only slowly over millions of years. Their isolation is so complete that sampling water from them requires techniques that maintain pressure, prevent contamination, and preserve the natural environment. Early attempts to reach these lakes raised concerns because of the difficulty in preventing contamination. Current plans focus on developing cleaner systems that can penetrate the ice without introducing foreign materials. The rivers connecting these lakes offer another layer of complexity. They allow nutrients, minerals, and possibly microbes to move between different parts of the subglacial system. Water flowing from one lake to another can carry chemical signatures that reveal the history of flow events. It can also provide clues about geothermal activity beneath the ice. When a river suddenly begins to carry more water, or changes its temperature, it might signal that the ice above has shifted, or that geothermal heat has increased in a certain area. Despite the complexity of this system, the lakes and rivers remain hidden from direct observation. No human has ever stood beside one. No camera has travelled through a subglacial river. Everything known about them comes from indirect measurements, radar signals, pressure changes in the ice above, and rare water samples obtained through carefully controlled drilling operations. This limited knowledge leaves large portions of the subglacial world unexplored. Scientists continue refining their models, developing new methods of detecting water beneath the ice, and preparing for future missions that might send robotic probes into these environments. The conditions within these lakes highlight just how different this hidden world is from anything on the surface. The water is cold but not frozen. The pressure is immense but stable. The darkness is absolute. There are no currents shaped by wind, no weather, no seasons. The environment remains steady except when the ice above shifts or water flows from one chamber to another. This stability creates a slow but steady world, one that moves in geological time rather than human time. Understanding these lakes and rivers explains why reaching the caverns beneath the ice is such a monumental task. Everything in the subglacial environment exists in delicate balance. Disturbing one part could alter the structure of the network or disrupt ecosystems that have existed unchanged for millions of years. Even the simplest interventions must be planned with precision. As this journey continues, the next step brings us to the immense forces that make the ice so unyielding. These forces do not just block access or alter drilling conditions, they define the pressure and structure of the world beneath, creating an environment where even the most advanced machines must fight to survive. Deep beneath Antarctica's frozen surface, where the weight of millions of years presses downward without interruption, the pressure becomes something difficult to compare to anything on the surface. It isn't like the pressure in deep ocean trenches, where water distributes the force in every direction. It isn't like the pressure inside solid rock, where minerals compact under immense geological strain. The pressure within the Antarctic ice sheet exists in its own category, shaped not only by weight, but by the way ice behaves under long-term compression. This pressure forms one of the greatest barriers to entering the caverns and waterways beneath the continent. It is what holds the entire structure together, what defines the shape and behaviour of the subglacial system, and what makes exploration a challenge that no current technology can approach casually. To understand this pressure, imagine layers of snow falling across the continent year after year. Each snowfall adds a thin layer that slowly becomes part of the ice as new layers accumulate above. As the snow compresses, air is squeezed out. The crystals grow larger, the ice becomes denser. After centuries of this, the upper layers sit atop lower layers that have already transformed into compact ancient ice. Over tens of thousands of years, these layers stack into a massive column that grows heavier with every passing century. It is this mass that creates the colossal pressure at the base. The deeper the ice goes, the more intense the pressure becomes, until it reaches a level that alters the physical behaviour of both ice and water. The pressure within the ice sheet does not simply push downward. Because ice is a deformable solid, it distributes pressure unevenly depending on temperature, crystal structure, and flow patterns. In some areas, the pressure creates a kind of internal stress that causes the ice to creep slowly outward. In others, it compresses the deeper layers so intensely that they flow in a pattern almost like thick paste. This combination of downward pressure and lateral movement shapes the network of subglacial lakes and rivers, forcing water into certain pathways and sealing off others. It is also what makes any attempt to penetrate through the ice incredibly risky, because drilling a hole creates a point of weakness in a system that has been stable for millennia. One of the most striking effects of this pressure is how it alters the melting point of ice. Under normal atmospheric conditions, ice melts at 0 degrees Celsius. But at the base of the Antarctic ice sheet, the melting point is lower because of the immense pressure. This means ice can remain solid even at temperatures where it would normally melt. At the same time, the thin films of meltwater that do form under this pressure remain liquid because the pressure prevents them from freezing again. The result is an environment where solid ice and liquid water coexist in delicate equilibrium. This balance is so finely tuned that even a slight change in temperature or pressure can cause water to refreeze or ice to melt unexpectedly. When scientists attempt to drill into this environment, they must account for the way the pressure will react to the new pathway. A borehole is not simply an opening, it is a structural interruption. The surrounding ice responds to it. If the pressure outside the borehole is greater than the pressure inside, the ice can begin to squeeze inward. This isn't a slow process. The walls of the hole can begin to deform almost immediately, narrowing the shaft and trapping equipment. To prevent this, the borehole must be filled with a fluid that matches the pressure of the surrounding ice. This requires precise calculations involving the density of the fluid, the temperature of the environment, and the rate at which the ice is likely to move. But finding a perfect match is nearly impossible. The fluid must be heavy enough to resist the pressure, but not so heavy that it pushes outward and fractures the ice. It must remain liquid in extreme cold. It must not contaminate the environment below. It must be pumpable through long hoses in sub-zero conditions. And it must maintain consistent pressure over a borehole that might extend thousands of meters. Even slight errors in these calculations can cause collapses, blockages, or sudden influxes of freezing water. This pressure also poses challenges for any equipment lowered into the borehole. Cameras, sensors, and sampling devices must withstand crushing forces. Their housings must be strong enough to resist deformation while remaining light enough to operate efficiently. Wires or fiber optic cables must resist tension from shifting ice. Every component must survive exposure to cold and pressure without losing integrity. Most underwater exploration devices are not built for such extreme conditions. They are designed for water pressure, not ice pressure, and the behavior of ice around an inserted object is far less predictable than the behavior of seawater. The pressure doesn't only act on the drilling equipment, it shapes the caverns and tunnels themselves. Some cavities remain open because the pressure is balanced by heat or water flow. Others exist only temporarily. A small change in the weight of the ice above can cause a chamber to collapse. A local increase in geothermal heat can melt a new cavity. Tunnels widen or narrow depending on how the ice shifts. This means the network beneath the ice is constantly evolving. A pathway detected by radar one year may have changed the next. A lake that was stable for millennia may drain suddenly. A cavern might expand or shrink without any surface sign. Understanding the way pressure shapes these hidden spaces is essential for imagining what exploration might someday look like. A robot navigating a subglacial lake must be built to withstand the weight of the ice overhead. Its movements could disturb the equilibrium, altering pressures and triggering unexpected changes in the environment. Even a small disturbance in a melt layer could alter the flow of water in a nearby tunnel. It is not simply a matter of reaching these spaces, it is a matter of interacting with them without destabilizing a system that has existed in balance for far longer than human history. The pressure also influences the chemistry of the water trapped beneath the ice. High pressure affects how gases dissolve, how minerals interact, and how water responds to heat. Lakes under these conditions can hold different concentrations of dissolved gases than surface lakes. They may have unique mineral contents shaped by the interaction between pressurized water and bedrock. These chemical differences may support microbial life or inhibit it. They also provide clues about how the water has moved over time, how long it has remained isolated, and what processes sustain its liquid state. As researchers develop better models of how pressure behaves within the ice, they are also working on technologies that might one day penetrate deeper into the sheet. These include hot water drills, thermal probes, and robotic systems designed to melt their way downward. But every method faces the same challenge: how to manage the immense pressure without triggering structural collapse or contaminating the environment. Even controlling the pressure at shallow depths is difficult. At greater depths, it becomes one of the most complex engineering problems in modern science. Perhaps the most daunting aspect of the pressure at the base of the ice sheet is its reliability. It doesn't change quickly. It doesn't fluctuate wildly. it doesn't give warnings. The pressure is steady, patient, and relentless. This means any mistake made during exploration has little room for correction. A small miscalculation in fluid density can cause a borehole to close. A minor flaw in equipment can lead to catastrophic failure. The pressure won't wait for a technician to fix a problem. It simply continues, crushing anything that cannot withstand its force. This unbroken freeze has held the subglacial world in its grip for millions of years. It has preserved ancient water, shaped hidden landscapes, and maintained ecosystems that may have evolved in complete isolation. It also stands as a reminder that the forces beneath Antarctica are not easily overcome. They require respect, caution, and an understanding of a world that operates according to rules far different from those at the surface. As the path continues deeper, attention shifts from the invisible pressures within the ice to the challenges faced by machines sent to explore it. These machines represent some of the most advanced technology humans have ever created. Yet even they struggle in a place where the ice itself is more powerful, more durable, and more persistent than anything built in laboratories or workshops. Machines built for Earth's harshest environments tend to earn reputations for reliability. Deep ocean submersibles withstand crushing seawater pressure. Mars rovers survive radiation, temperature swings, and dust storms. Arctic vehicles push through blizzards and brutal cold. Yet even these machines would fail quickly in the hidden underworld beneath Antarctica, because nothing on the surface fully prepares technology for an environment where the ice is stronger than steel, where pressure squeezes from every direction, where cold drains power from any battery, and where a single mechanical weakness becomes a permanent entombment. Beneath the Antarctic ice sheet, machines don't just malfunction, they surrender, one component at a time, long before the ice shows the slightest sign of giving way. To understand why machines struggle, it helps to picture the conditions they are expected to face. A probe descending through a borehole must tolerate extreme cold near the surface, rising temperatures as it travels downward, steadily increasing pressure, and constant vibrations from shifting layers of ice. It must maintain communication with the surface, operate precisely, avoid contaminating the environment, and survive long enough to reach its destination. It sounds manageable in theory, but in practice it becomes a list of engineering nightmares. The cold is the first obstacle, and it begins working against machines immediately. Even at the surface of Antarctica's interior, temperatures can fall below -60 degrees Celsius. At these temperatures, metals contract unpredictably. Plastics become brittle and snap if flexed. Lubricants thicken to the consistency of wax. Hydraulic systems lose efficiency. Seals become stiff and crack under pressure. Electronics must be insulated constantly, and even then, the cold creeps inward through cables and housings, slowing processes, draining batteries, and pushing systems toward failure. A machine that runs flawlessly in a controlled cold room at home might last only minutes in open Antarctic conditions. Teams working on the surface use heaters, insulated enclosures, and constant monitoring to keep equipment functional. But once a probe begins descending into the ice, all of this external support disappears. The machine must rely entirely on its own thermal protections. If its internal heaters fail, even briefly, cables can freeze to the walls of the shaft, sensors can lock up, moving parts can seize, batteries can lose charge so rapidly that mission plans become impossible, and because the descent through thousands of meters of ice is slow, the machine may spend days in this freezing environment, each moment giving the cold more time to weaken it. As the probe goes deeper, it encounters another enemy: pressure. The weight of the ice above is immense, far greater than the pressure inside deep oceans. Ice pressure does not act like water pressure. It pushes in from all directions while also deforming the material surrounding the probe. At certain depths, the ice behaves like a thick flowing substance under stress. This means that if a machine stays still for too long, the ice can begin to squeeze around it. reducing clearance in the borehole. If the machine is tethered, the cable can become lodged in narrowing passages. If the machine is untethered and relies solely on communication signals, it may quickly lose the ability to send or receive instructions. The pressure also affects the borehole itself. As teams drill downward, they must fill the shaft with a fluid that prevents collapse. This fluid must match the pressure exerted by the surrounding ice. If it's not dense enough, the ice squeezes inward. If it's too dense, it pushes outward and causes fractures. Even when the fluid is perfectly balanced, the walls of the borehole are not stable. Slight shifts in the ice can warp the shaft, making it uneven. A probe navigating this path must be robust enough to withstand collisions, scraping surfaces and sudden narrow sections, all without being damaged or trapped. In some drilling attempts, the borehole freezes behind the probe as it descends. This creates a dangerous scenario. If the machine needs to be pulled back up due to a malfunction, the refrozen sections can prevent recovery. The deeper the probe goes, the less likely retrieval becomes. A single jammed thruster or malfunctioning cable may result in losing the entire machine forever. Even successful missions risk losing equipment to the ice long before any meaningful data is collected. The deeper layers of ice present additional complications. Temperatures rise slightly due to geothermal heat, which sounds like a benefit until the probe encounters water that can refreeze unpredictably. Meltwater forming along the borehole walls can turn to ice again in moments, locking instruments in place. Some drilling approaches use hot water jets that melt the ice ahead of the probe, but this introduces a different risk. The water may refreeze too quickly, sealing the borehole from behind and trapping the equipment in a narrowing column with no escape. Machines must also navigate the chemical environment of the deep ice. Even though it's frozen, the ice contains salts, gases, and particles that have collected over hundreds of thousands of years. These materials can corrode metal surfaces, contaminate sensors, or interfere with mechanical systems. Subglacial water is even more challenging. It may carry dissolved minerals from bedrock, pressurized gases, or unusual chemical concentrations. A robot entering these waters must be able to function without reacting chemically with the environment or degrading over time. Communication becomes a persistent problem. Radio signals cannot penetrate thick ice reliably. Once a machine goes more than a few meters into the ice, any signal weakens dramatically. For this reason, most deep probes require tethered systems with fiber optic cables. These cables must withstand pressure, cold, and movement inside the borehole. They must not freeze, kink, or snap. If they do, the probe becomes blind and unreachable. Designing cables that can survive this journey is one of the most difficult engineering tasks in Antarctic exploration. Some systems attempt to use acoustic signaling, sending vibrations through the ice itself, but this method has severe limitations in resolution, data speed, and range. The problem becomes even more significant when machines reach the subglacial lakes and rivers themselves. These environments are sealed by the ice above, contain water under intense pressure, and may remain completely still for long periods. A robot entering a lake must be able to adapt to conditions no human has experienced firsthand. It must tolerate full submersion in freezing water, navigate without natural light, and remain structurally sound despite pressure that would crush conventional equipment. Thrusters must work reliably without stirring up sediments that could damage sensors. Cameras must function in total darkness. Sampling devices must operate without contamination. Every component must function perfectly, because there is no possibility of repair once the robot is released. Some experimental designs include cryobots, machines that melt their way downward through the ice. These systems use heat to create a vertical tunnel, allowing the robot to descend gradually. While promising, cryobots face significant challenges. They must generate enough heat to melt ice continuously for long periods, without overheating internally. They must prevent refreezing behind them. They must avoid consuming too much fuel, and they must withstand sudden changes in ice structure. such as layers with different densities or impurities that conduct heat unpredictably. If a cryobot encounters a cavity or water chamber unexpectedly, it can be damaged by the drop in pressure or by turbulent water refreezing around it. Another type of machine under development is the autonomous underwater probe intended for subglacial lakes. These robots face many of the same challenges as deep-sea vehicles, but must operate under far more restrictive conditions. They cannot surface to reset systems. They cannot rise to a ship for repair. Their mission may require navigating through narrow passages or layered water columns with varied salinity and temperature. If they become trapped by ice, bedrock, or slushy deposits, there is no way to retrieve them. Even surface machines, those used to support drilling and research, face staggering difficulties. Snowcats, tractors, and generators must operate in temperatures that cause diesel fuel to gel unless it is treated constantly. Rubber tracks stiffen and crack. Electronic controls freeze. Metal components become brittle. Any repair requires careful preparation because tools become too cold to handle, and exposed skin freezes instantly in heavy winds. A small mechanical issue can halt a major operation, and every fix takes longer in an environment where even holding a wrench becomes painful within seconds. This is why every major Antarctic expedition brings redundant systems. For every crucial machine, there are spares. Spare sensors, spare cables, spare heaters, spare pumps, spare components of all kinds. Teams anticipate failure as part of their operations because Antarctica's ice is consistent in only one way. It breaks machines long before it shows signs of yielding itself. Despite these obstacles, engineers continue refining technologies designed for this environment. They test materials that resist cold, lubricants that remain fluid at extreme temperatures, cables that maintain flexibility under pressure, and autonomous systems that adapt to unpredictable conditions. Each advancement brings humanity closer to sending a machine deep enough to explore the subglacial caverns. But progress is slow because the ice remains uncooperative. It shifts, squeezes, freezes, corrodes, and overwhelms anything that tries to pass through it. As the challenges of machinery make themselves clear, attention turns naturally to the human element. If the most advanced equipment struggles to survive Antarctic conditions, moving humans into these depths becomes even more unthinkable. Yet curiosity persists, and part of that curiosity leads us to consider the logistical and physical extremes that make the continent not only difficult for machines but nearly unfathomable for human explorers. Antarctica is unlike any other place on Earth because it imposes limits not only on technology, not only on engineering, but on human presence itself. On most continents, even the harshest environments offer some route to safety: a road, a settlement, a rescue service, or at least a way for assistance to arrive within hours or days. On Antarctica's interior, none of that exists. Once someone travels far into the continent, they are not simply far from help, they are beyond its reach. The combination of unrelenting cold, enormous distance, and complete isolation creates a setting where even routine tasks become risky, and where a serious emergency can escalate into an impossible situation within minutes. For anyone imagining an expedition into the caverns below the ice, it is crucial to understand why the surface alone represents an environment that humans cannot handle without the most careful planning and support. The cold is the first and most immediate threat. At the heart of Antarctica, temperatures can drop below -80 degrees Celsius. In these conditions, metal becomes dangerous, steel grows brittle, aluminum contracts and warps, copper wiring stiffens and can fracture if bent. Even the small metal components inside machines, screws, connectors, springs, become fragile in ways that are difficult to predict. If a vehicle breaks down, its parts may crack when handled. Tools left outside for only a short period can become too cold to touch safely. Even a metal water bottle carried in a thick glove can freeze to the outer layer if held for too long, requiring the person to peel it away carefully to avoid injury. Plastic and rubber, often used for insulation or engineering flexibility, fare no better. Rubber hoses harden, cracking under even slight pressure. Plastic casings fracture if bumped. Electronics housed in plastic compartments suffer constant stresses from the temperature difference between the warm interior and the freezing exterior. As this difference grows, the materials separate or warp, allowing cold air to creep in. Over time, the cold wins every contest. A machine brought to Antarctica might function perfectly one day, and become completely inoperable the next, not because of misuse or mishandling, but simply because its materials cannot withstand the temperature range. Vehicles designed for polar travel require constant maintenance. Their engines must run regularly, even when not in use, to prevent fluids from freezing. Fuel must be treated to remain usable. Filters clog with crystals. Batteries drain far faster than normal and must be heated just to retain a charge. Every action requires preparation. Starting an engine is not a matter of turning a key. It is a sequence of heating steps, checks, and adjustments. A failure during any part of this process can leave a team stranded in a place where the temperature outside a stalled vehicle can kill exposed skin in less than a minute. While cold alone would already make Antarctica a place too hostile for unprotected humans, the remoteness amplifies every danger. Most of the continent has no permanent human presence. Research stations exist, but they are separated by enormous distances. Some are hundreds, even thousands of kilometers apart. Between them lie vast plains of featureless snow, ridges carved by wind, and steep crevasses hidden under thin crusts of ice. There are no roads, no markers, no natural signs to navigate by. Even in clear weather, visibility stretches only as far as the horizon, and the landscape looks identical in every direction. Rescue operations depend on weather conditions, which turn unpredictable within minutes. A plane cannot land in a storm. A helicopter cannot fly in winds that gust across the plateau. Even ground vehicles may be unable to move when visibility drops to almost nothing during a whiteout. A team in distress might activate an emergency beacon, but that does not guarantee help can arrive. Rescue crews may have to wait days before travelling becomes safe. During that time, the stranded individuals must rely entirely on their own supplies and shelter. Any miscalculation in fuel, food, or equipment can become fatal. Communication is another difficulty. Satellite links can transmit messages, but they rely on clear skies and stable equipment. In a place where electronics freeze or malfunction easily, communication failures become common. A team might believe their distress signal was received when it was not, or their equipment may fail before they can report their situation. The remoteness of the continent means that even when communication is perfect, the physical distance between people makes any response slow. There are no quick interventions. Everything happens on a timeline dictated by weather and geography. Medical emergencies add another layer of risk. At the surface stations, some medical facilities exist, but they are limited. They can handle minor injuries or illnesses, but not major surgeries or complex treatments. If someone suffers a severe accident or health crisis deep in the interior, evacuation may not be possible for days or weeks. Even if a plane can land at a nearby station, reaching that station from a remote field camp may require long overland travel in brutal conditions. In many cases, the only option is stabilization and waiting, hoping conditions improve in time. The cold also affects the human body directly. Exposed skin freezes within seconds. Breathing becomes painful as icy air dries the throat and lungs. The body burns enormous amounts of energy just staying warm. Frostbite can begin even through multiple layers of clothing if sweat accumulates and freezes. Hypothermia is a constant threat. In these conditions, simple mistakes become severe hazards. If someone removes a glove for too long, their hand may lose dexterity. If a zipper jams or a buckle breaks, fixing it becomes nearly impossible with numb fingers. Even eating must be planned carefully, because food freezes solid and must be warmed before it can be consumed. Fatigue also sets in more quickly than expected. The cold drains energy, the altitude at parts of the plateau lowers oxygen levels, and the landscape's uniformity can dull alertness. A tired person becomes less precise with equipment, more likely to make mistakes, and slower to react to emergencies. All of these factors multiply the risks present in an environment where help may not arrive until long after a problem begins. The psychological aspect of remoteness cannot be ignored either. The absolute silence, immense distance from civilization, and constant presence of danger can wear on even the most experienced explorers. Days may pass without any sign of change. Storms can trap teams inside shelters for long stretches, leaving them with little to do but wait out the weather. This isolation can affect judgment and mood, making routine decisions feel overwhelming and complex choices feel impossible. Even the most prepared teams face unforeseen complications. Vehicles become buried under drifting snow, equipment malfunctions in ways that cannot be diagnosed in the field, fuel depots become inaccessible, tents tear in high winds, drilling towers tilt as the snow beneath them shifts. Teams may need to adjust plans quickly, but any change introduces new risks. A short detour may cross unknown terrain. An alternate route may pass near hidden crevasses. A delay may expose equipment to colder conditions than anticipated. All of this is happening on the surface, and the surface is the easy part compared to the caverns beneath the ice. If rescue is almost impossible on the open plateau, it becomes truly impossible in the subglacial world. No helicopter can dive into a borehole. No vehicle can descend through thousands of meters of ice. No team can reach a trapped robot, let alone a trapped person. This reality shapes every decision made by Antarctic researchers. They know the limits. They know that a single, carelessly planned step can lead to a situation without a solution. And they plan accordingly, building redundancy into every system, adopting strict protocols, and placing safety above every scientific goal. This remoteness also explains why exploration efforts rely so heavily on technology, automation, and remote sensing. Human presence is limited not only because the ice is unforgiving, but because any incident involving personnel in remote areas creates risks far greater than those faced in more accessible environments. Engineers design probes that can operate independently because sending a person into these depths is not an option. The ice is too cold for humans to tolerate directly, the distance is too far for timely rescue, and the environment reacts too unpredictably for navigation without constant monitoring. Even if a machine could somehow carry a human into a cavern, getting them out again would be nearly impossible. The ice might refreeze behind them, the shaft might collapse, the equipment might fail, communication lines might break. Every hazard that threatens a robot would be exponentially more dangerous to a human who cannot survive even brief exposure to the conditions below. All of this shows why Antarctica remains one of the last true wildernesses on Earth, one that limits human access not out of hostility but through sheer physical reality. It is not a place designed for human life. It is a place where the planet's most extreme forces operate openly, without compromise. And as we continue exploring the hidden world below, the next step draws us toward the mysteries of what might actually live in these dark, remote depths. Organisms that have adapted to survive conditions that challenge even the most advanced machines. Beneath the vast Antarctic ice sheet, in waters that have been sealed off from the sky for millions of years, the idea of life feels both impossible and strangely inevitable. It's difficult to picture creatures living in total darkness, in water pressed by ice thicker than entire mountain ranges, in ecosystems without sunlight, plants, or the usual cycles that sustain biology on the surface. And yet, every time scientists look deeper into this hidden world, they find hints that something may indeed be alive down there. Something adapted to conditions so extreme that it challenges our understanding of what life on Earth can endure. These possible organisms are not monsters or mythical beings. They are likely small, subtle forms of life, but strange in a way that reflects their environment. Life that never sees light, never rises to the surface, and survives using methods that no familiar ecosystem relies on. Before exploring what these organisms might be like, it's important to understand the environment they inhabit. Subglacial lakes are not open basins with room to swim freely. They're tightly sealed systems where temperature, pressure and chemistry follow strict rules. The water remains liquid because of pressure and geothermal heat, yet it sits close to freezing. It contains minerals dissolved from the bedrock, gases trapped under ice, and sometimes salts that seep into the system from microscopic fractures. There is no sunlight. Photosynthesis is impossible. Oxygen levels can be extremely low or non-existent. Nutrients must come from geochemical sources rather than organic debris. This is the context in which life, if it exists, must survive. The first hints of such life came not from Lake Vostok or other large subglacial lakes, but from smaller pockets of water trapped between ice layers and at the base of ice streams. Samples taken from these small pockets revealed bacteria living in thin films of meltwater. These microbes were not dormant. They were metabolically active, consuming minerals, respiring and reproducing extremely slowly. Their presence suggested that life could indeed survive in the dark depths under the ice, relying on chemical processes instead of sunlight for energy. This finding raised an even bigger question. If small pockets of water in extreme conditions could sustain life, what might exist in the massive lakes and interconnected rivers far below? Lake Vostok, the most famous of Antarctica's hidden lakes, has been sealed beneath nearly 4 kilometers of ice for millions of years. Its ecosystem has been completely isolated from the rest of the world. Early drilling attempts there were controversial because of the risk of contamination. Despite the difficulty of obtaining clean samples, researchers eventually found signs of microbial DNA in water extracted from near the lake. While the samples were not perfect, and the risk of contamination complicated interpretations, the consistency of the results across multiple studies suggested that microbes may indeed inhabit the subglacial environment. These microorganisms appear to be adapted to extreme cold, low nutrients, and high pressure. Some may consume minerals from the lake's sediments. Others might process dissolved gases. Their existence hinted at ecosystems built not on sunlight, but on chemical reactions between water, rock, and trapped gases. In other subglacial lakes, scientists have detected signs of microbial communities that rely on entirely different energy sources. Some microbes appear to feed on hydrogen produced by water-rock interactions. Others may thrive on sulfur compounds. In some regions, methane trapped in the ice could serve as an energy source for methanotrophic organisms, microbes that consume methane and convert it into chemical energy. These types of organisms are known on the surface but typically inhabit deep-sea vents, underground aquifers, or other oxygen-poor environments. Their presence beneath Antarctica would suggest that life finds ways to persist, even where conditions seem nearly incompatible with survival. One of the most intriguing possibilities is that some subglacial lakes may harbour layered water columns with different chemical profiles. The upper water might be fresher, closer to the ice, while lower layers could contain more minerals and gases drawn from the bedrock. This separation could create microenvironments where different microbial species thrive. In some scenarios, organisms might cycle between layers, depending on temperature, chemistry, or nutrient availability. Over time, such microenvironments could support communities of organisms with distinct functions, forming a miniature ecosystem unlike anything found on the surface. Even more surprising are discoveries made in subglacial rivers and streams. When scientists drilled into these systems, they expected to find sterile water or a few extremely hardy microbes clinging to survival. Instead, they found active microbial communities with surprisingly diverse metabolisms. Some microbes were capable of breaking down iron compounds. Others processed sulfur or produced gases that could support additional forms of life. These discoveries suggested that the hidden waterways beneath Antarctica are not barren tunnels, but part of a dynamic ecosystem driven by slow, geological and chemical processes. All of this evidence contributes to a growing picture of what the strange creatures beneath Antarctica might be like. They would be microscopic, not visible to the naked eye, living slowly in the cold darkness. They would rely on chemical reactions with minerals, gases, and geological substrates rather than sunlight or organic material. They would reproduce at extremely slow rates due to the limited availability of energy. Their DNA might be uniquely adapted to dealing with cold, pressure, and isolation. They may form biofilms, thin layers of microbial communities that attach to surfaces like ice walls or sediments. These biofilms could be some of the most extreme forms of life on Earth, surviving without light or external organic input for millions of years. Yet there is also the possibility of something slightly larger. Some scientists speculate that small multicellular organisms, simple ones such as nematodes, tardigrades, or microscopic crustaceans, could exist in subglacial environments, though this remains unproven. On the surface and in frozen soils, tardigrades and nematodes have been found surviving long periods of freezing and starvation. If any such organisms were trapped in a subglacial lake early in Antarctica's history, and if conditions were stable enough, they might have adapted to the dark, high-pressure waters. But this idea remains purely speculative. No direct evidence has been found for complex organisms below the ice, and the environment is so nutrient-limited that sustaining larger life forms would require extremely efficient survival strategies. Even without larger organisms, the microbial world under the ice would still be remarkable. It would represent one of the oldest, most isolated ecosystems on Earth, shaped entirely by internal forces rather than surface influences. Studying such life could provide insights into how early Earth organisms survived before the atmosphere and sunlight became suitable for widespread biological activity. More importantly, it could serve as a model for life on icy moons elsewhere in the solar system. If microbial ecosystems survive under Antarctica's ice, then similar systems might exist beneath the icy crusts of Europa, Enceladus, or other frozen worlds. The challenge, of course, is proving that these organisms exist without contaminating their environment. Sampling water from subglacial lakes requires drilling systems that introduce no foreign microbes, chemicals, or heat disturbances. Even slight contamination could disrupt the native ecosystem or distort scientific results. Researchers must sterilize equipment carefully, use purified fluids, and design probes capable of collecting samples without altering the water's chemistry. These constraints make direct exploration extremely difficult. Even with perfect technology, the pressure beneath the ice poses another barrier. Water in subglacial lakes is under tremendous force. If a probe enters carelessly, a sudden change in pressure could cause freezing, mixing, or chemical reactions that obscure signs of life. To study these ecosystems properly, scientists must design equipment that interacts with the environment gently, maintaining pressure, temperature, and chemical stability. Achieving this is one of the greatest engineering challenges in modern science. Despite the difficulty, the search continues. Scientists have collected enough indirect evidence to build reasonable hypotheses about what might live beneath the ice. The organisms they imagine are not dramatic or visually striking. They are not creatures with eyes adapted to darkness or bodies shaped by vast underwater caverns. Instead, they are tiny, resilient forms that endure in places where energy moves slowly and where life must stretch every resource to survive. These possible organisms tell a story of persistence, of survival against cold, pressure, and isolation. They reveal how life adapts to conditions far beyond the comfort zones of most known species, and they push us to rethink where life can exist on Earth and elsewhere. As the idea of living organisms hidden in darkness becomes more plausible, the next question turns to how scientists even attempt to detect these creatures in environments that resist direct observation. This shifts the journey deeper into the reasons why even satellites, with all their power and sensitivity, cannot fully reveal what is waiting below the ice, leaving entire ecosystems partially hidden and fueling the curiosity that drives further exploration. From high above the Earth, satellites can watch storms form across continents, track ocean currents as they shift, map deserts, forests, mountains, and even the tiny changes in vegetation that mark the passing of seasons. They can see cities glowing at night, ships crossing oceans, and volcanic plumes rising into the atmosphere. But when they look toward Antarctica, something changes. The surface appears clear enough, an expanse of white shapes, faint shadows, drifting ice, and long ridges sculpted by wind. Yet the moment their instruments attempt to look deeper, into the ice, through the frozen sheet, toward the hidden world below, they begin to lose the ability to interpret what they're seeing. This isn't because satellites lack sophistication, it's because the ice itself refuses to reveal what lies beneath, scattering signals, distorting readings, and blurring information so thoroughly that deeper structures remain little more than estimations and educated guesses. The difficulty begins with the nature of satellite sensors. Many instruments rely on electromagnetic signals, light, microwaves, radio waves, that bounce off surfaces and return information about what they've encountered. On land, these signals reflect from soil, rock, vegetation and water in ways that satellites can interpret and convert into detailed images. Under the ice of Antarctica, however, these signals behave unpredictably. The ice is not uniform. It is a mass of layers, each with its own density, crystal structure, impurities and internal stresses. When a satellite signal enters the ice, it doesn't travel in a straight line. It bends, refracts, scatters, and weakens as it passes through different layers, each one affecting the signal differently. By the time the signal reaches the bedrock, or a cavern, or a subglacial lake, only a small fraction remains. And even that tiny portion is distorted by the thousands of meters of ice it travelled through. Different methods attempt to penetrate this barrier, each with its own strengths and limitations. Radar satellites send long, wavelength pulses through the ice to bounce off the ground below. Sometimes they succeed, revealing the rough shape of bedrock or large lakes. But radar does not produce high-resolution images deep beneath the ice. Instead, it creates broad outlines and rough maps. These maps can show depressions, slopes, and large formations, but they cannot reveal the fine details, the size of a chamber, the shape of a tunnel, the presence of a narrow river, or the texture of an ice wall. Radar penetrates deep enough to sense the general structure, but not enough to visualize the complex labyrinth hidden underneath. Even when radar readings do reach the base of the ice sheet, interpreting the signals is incredibly challenging. Ice crystals vary in size, shape, and orientation. Some layers contain bubbles, others contain dust or volcanic ash. These differences cause parts of the signal to reflect and others to refract in unexpected ways. Signals bounce around inside the ice, creating echoes that overlap and blend. A clear reading becomes a pattern of overlapping reflections that must be analysed with models and computational techniques. Scientists can reconstruct some information from these echoes, but the results are approximations, not precise depictions. Another method uses satellite gravimetry, measurements of extremely small changes in Earth's gravitational field, to infer what lies below the ice. This technique can reveal large-scale features such as whether a region holds a deep valley or a basin filled with water. But gravimetry has low spatial resolution. It can detect general shapes but cannot identify specific details. It cannot map small lakes or narrow tunnels. It cannot show whether a cavity is filled with water or air or slushy mixtures. It cannot reveal whether the bedrock is smooth or jagged. Gravimetry helps paint the broadest strokes of the picture, but most of the finer details remain hidden. Satellite altimetry, measuring the height of the ice surface, offers another indirect way to understand what lies beneath. When a subglacial lake fills with water, the surface above rises gently. When the lake drains, the surface sinks. Satellites can detect these elevation changes with remarkable precision. By tracking these changes, scientists can identify which lakes are active, how much water they hold, and sometimes how they're connected to nearby lakes. But this method cannot reveal the shape of the lake or the pathways that connect the hidden waterways. It only provides information about how the surface responds to changes far below. It is like watching a floating object rise and fall, knowing something beneath it is shifting, but not being able to see what that something is. Optical satellites, the ones that take photographs similar to those captured by cameras, are completely blind to the subglacial world. They can capture surface features, the edges of glaciers, crevasses and cracks in the snow, but that is all. Ice is opaque to visible light. Even the clearest blue glacial ice becomes completely unreadable after only a short depth. None of the complexity beneath the ice shows up in optical images. The hidden world remains invisible. Another challenge comes from the way ice absorbs and scatters energy. Unlike water or rock, ice's internal structure is constantly shifting in subtle ways. Temperature gradients cause crystal boundaries to reorganize. Pressure changes alter the density. Impurities move and settle through the layers. All of this affects how signals travel. A satellite might detect clear reflections from ice in one region, but receive almost no information from another area with the same nominal thickness. Small differences in ice structure cause major differences in signal behavior. This randomness creates blind spots, even in places where scientists expect conditions to be ideal for remote sensing. Even if a satellite signal reaches a subglacial lake or cavern, the boundary between ice and water creates reflections that don't behave as expected. The interface is not perfectly smooth. It contains tiny imperfections where pressure, temperature and ice flow distort the surface. Some regions reflect signals too strongly, creating a glare of sorts that obscures anything beneath. Other regions absorb signals almost completely, hiding whatever lies below. Meanwhile, movement in the ice, however slow, changes these boundaries over time, adding another layer of variability. This makes it difficult to reconstruct consistent images even when multiple satellite passes gather data over the same location. Seismic imaging could, in theory, reveal more detail, because sound waves travel through ice differently than through water or rock. But seismic techniques require sensors placed directly on the ice surface, not satellites in orbit. These sensors must be installed manually during expeditions, sometimes across vast areas, and are limited by the logistics of reaching remote regions. Even when deployed successfully, seismic surveys produce data that require interpretation through layered models, offering general structures but not exact shapes. And just like radar, seismic waves scatter unpredictably through the ice. Another issue is the sheer depth of the ice sheet. The deeper the target, the weaker the returning signal. Some parts of the ice sheet are more than 3 kilometers thick. Any signal that travels through such depth must endure scattering, absorption and reflection. By the time it returns to the satellite, it may be too weak to interpret, or it may contain too much noise to be useful. Even the most powerful satellite-based radar cannot overcome this limitation entirely. The deeper the hidden world lies, the more it remains beyond reach. Beyond the technical limitations, there is also the fact that many features beneath the ice are simply too small or too complex to detect from orbit. Caverns may be narrow, twisting spaces with irregular shapes. Tunnels may be only a few meters wide. Lakes might be shallow or divided into multiple pockets by ridges in the bedrock. Satellites excel at mapping large, continuous structures, not intricate, fragmented ones. The labyrinth beneath Antarctica contains countless features far smaller than the resolution limits of any satellite. Because of all these obstacles, scientists combine multiple kinds of data: radar, gravimetry, altimetry, seismic results, and computer modelling, to build partial maps of the subglacial environment. These composite images reveal more than any one method could, but they still leave gaps. Entire regions remain uncertain. Some lakes have been detected only because of small shifts in the ice above them. Some valleys and ridges beneath the sheet are inferred from glacial flow patterns rather than directly observed. In many areas, the maps resemble outlines, sketches, and approximations rather than detailed depictions. Even with decades of satellite observations, the world beneath the ice remains a patchwork of knowns and unknowns. Scientists can identify likely pathways but not confirm their shapes. They can detect large lakes but not the full extent of the tunnels that connect them. They can sense depressions in the bedrock but not the detailed contours. They can observe changes in the ice surface but not the exact events happening underneath. The truth is that satellites give us just enough information to know the hidden world is there, but not enough to understand it fully. This limitation shapes how exploration must proceed. Because satellites cannot truly see what lies underfoot, researchers must rely on careful drilling, indirect measurements, and cautious navigation. They must accept uncertainty and adjust plans based on results that may shift as new data emerges. And as scientists continue to refine their models and technology, the next major question turns toward the human story. Why, despite the overwhelming challenges, the dream of reaching this hidden world persists? And what drives people to keep imagining a future where the secrets beneath Antarctica's ice might finally come to light? For as long as humans have looked at the world with curiosity rather than fear, there has been a pattern that repeats itself across generations. People see something hidden, distant, unreachable, or sealed away, and they begin to imagine what it would be like to cross that boundary. It happened with the deep ocean. It happened with the poles. It happened with mountains once considered impossible to climb. And it is happening now with the vast dark world beneath Antarctica's ice. Even though the environment is one of the most hostile on Earth, even though the cold destroys machines and the pressure overwhelms our best engineering, even though satellites cannot reveal what lies below, and no rescue is possible if something goes wrong, the idea of reaching that world still holds a powerful sway over researchers, explorers, and dreamers alike. This desire is not about adventure in the traditional sense. It is not about planting a flag, proving endurance, or conquering the unknown. Instead, it comes from the quieter human instinct to understand something fundamental, to see how nature works in its most isolated and untouched forms. Antarctica's subglacial world is a place where Earth has kept parts of its story sealed for millions of years. The water that exists in those hidden lakes has been disconnected from the atmosphere since before early human ancestors walked upright. The sediments that line those lake beds contain chemical clues and geological markers untouched by light, wind, or weather. And if life has evolved in these environments, it would represent one of the most extraordinary biological discoveries ever made, a living record of survival in conditions that push the limits of what life can endure. For scientists, this is not just another mystery. It is a rare chance to observe Earth as it existed long before humans changed its surface, built cities, or altered its climate. The hidden world below the ice preserves something ancient, something not quite frozen in time but protected from the rapid changes happening above. Reaching it would mean accessing an archive of natural processes, chemical reactions, and biological adaptations that operate independently from surface influences. Understanding it would not only teach us about Earth's past, but help us imagine what environments might be like on distant icy moons where sunlight never reaches the subsurface oceans. The dream of reaching this world persists because of what it represents. It is the last major frontier on our own planet, one of the few remaining places where entire ecosystems might exist that no one has ever seen, touched, or measured directly. Even the deep ocean, for all its mysteries, has been visited by submarines. Outer space, though vastly unexplored, has been entered by human spacecraft and satellites, but the caverns beneath Antarctica remain closed. No person has stood in those spaces, no camera has drifted through their waters, no direct images exist of their walls or their sediments. They are as hidden now as they were during ancient eras when the world was still young. Reaching them is not only a scientific challenge, but a psychological and emotional one. There is something deeply compelling about the idea of touching a place that has never been disturbed, where nature has been left to evolve without interruption. It reminds people that the planet is still capable of surprising us, still capable of withholding secrets even in an age where so much information is available instantly. In a world where satellites map coastlines and drones scan forests, the existence of a place that resists all attempts at mapping suggests that mystery still has a role to play in human curiosity. But the human dream of reaching this world is also shaped by practicality. Scientists know that if they can understand how life survives in subglacial ecosystems, they might gain insight into how life could exist beyond our planet. The icy moons of Jupiter and Saturn, Europa and Enceladus, contain vast oceans trapped beneath thick crusts of ice. If life exists there, it would likely resemble the life found in Antarctica's subglacial lakes, far more than life on Earth's surface. Studying the hidden Antarctic world could become a test run for future missions to these distant places. It is a chance to practice methods, refine technology, and learn how to explore environments that cannot be approached with conventional tools. This makes Antarctica not only a scientific frontier, but a training ground for the search for life in the universe. Despite these motivations, the reality of reaching this world is filled with uncertainty. Every attempt to explore beneath the ice must be planned with extraordinary precision. Drilling operations require years of preparation. Environmental protections must be absolute to avoid contaminating ecosystems that may have existed in isolation since long before humans evolved. Engineers must design machines capable of descending through freezing shafts, maintaining pressure, avoiding damage, and functioning independently for long periods. Scientists must build protocols for collecting samples without altering their chemical or biological integrity. Each step requires caution, patience, and the ability to accept that failures will be common and progress slow. But this slow progress is not discouraging. For many researchers, it is part of the appeal. Antarctica demands humility. It forces scientists to acknowledge the limitations of their tools and the need to adapt to an environment that resists intrusion. That humility is rare in modern exploration, where advanced technology often gives the illusion that nothing is beyond reach. In Antarctica, nothing comes easily. Nothing yields quickly. Everything must be earned. And this creates a kind of respect, a recognition that the natural world still holds power that outweighs human determination. The people who dream of exploring this hidden world are not reckless or romanticizing danger. They fully understand the risks. They know that no human will descend into the caverns, that any exploration must rely on machines capable of operating where people cannot survive. They know that a robot sent into a subglacial lake may be lost forever. They know that the ice could shift, refreezing behind a probe and trapping it. They know that a single miscalculation in pressure, temperature, or timing could undo months or years of work. Yet the possibility of uncovering something no one has ever seen keeps them moving forward despite these challenges. Curiosity plays a large role, but responsibility does too. The more the climate changes, the more scientists want to understand the history preserved in ice. Subglacial lakes hold records of temperature, precipitation, mineral deposition, and chemical composition that reflect Earth's long-term climate cycles. If these environments are disturbed or altered before they are studied properly, valuable information could be lost forever. The dream of reaching them is not just about seeing their beauty or understanding their strangeness. It is about capturing data that may help future generations understand what is happening to the planet and how to prepare for changes that surface environments may not fully record. Even beyond scientific value, the idea of a world locked beneath ice captures something deeply human. The desire to explore not for conquest or fame, but for understanding. People want to know what is there because the unknown holds a certain pull, a quiet sense of possibility that survives even in the modern world. The deeper the mystery, the stronger the pull becomes, and the world beneath Antarctica is one of the deepest mysteries still remaining. This dream also endures because each discovery brings new questions rather than closing the door on curiosity. When scientists identified subglacial lakes, they wanted to know how many existed. When radar detected rivers flowing between them, they wanted to know their routes. When sediment cores suggested microbial life, they asked how these organisms survive. When satellite altimetry revealed shifts in the ice surface, they wondered what changes beneath caused them. Each answer leads to more questions, each discovery to more possibilities. The dream grows not from the idea of a single revelation, but from the realization that exploring the subglacial world will take generations. Even the limitations of technology inspire creativity. Engineers imagine cryobots that can melt downward slowly, tethered by fiber optic cables strong enough to withstand pressure. They design systems that sterilize themselves repeatedly to avoid contamination. They envision probes that can separate from their melt channels and swim freely through the water once they reach a lake. These designs are ambitious, sometimes bordering on science fiction, yet they continue to evolve as materials and techniques improve. What was impossible 20 years ago is now being tested. What is impossible today may become achievable soon. Still, despite all this progress, the dream remains grounded in patience. Researchers know they are moving at the pace the continent allows. Antarctica sets the rhythm. It dictates how quickly machines can be deployed, how long drilling can continue, when helicopters can land, and when crews must wait out storms. It decides which paths remain open and which remain sealed. In this way, the quest to reach the hidden world becomes a partnership between human persistence and the slow certainty of nature. And through this partnership, a quiet optimism grows. Not the kind built on naive expectations, but the kind that comes from decades of slow progress. Imperfect, uncertain, but steady. Every survey, every model, every drill core, every radar pass, every measurement taken on the ice adds another piece to a story that is still unfolding. The dream is not about reaching the destination quickly. It is about continuing the journey with the understanding that some discoveries take a lifetime, or many lifetimes, to achieve. The world locked beneath Antarctica is waiting, not in the dramatic sense of a treasure to be uncovered, but as a part of Earth that will eventually reveal itself when approached with enough patience, care, and respect. It remains sealed for now, and likely for many years to come. But the human desire to understand it is as persistent as the ice that guards it. That persistence, slow and determined, mirrors the very forces shaping the continent. Both move steadily, both endure, and both will continue, one above and one below, until the moment humanity finally sees the hidden world for what it truly is,